Welcome back, everybody. So we are going to finish Module 9 here by looking at rational equations and inequalities. And so for solving rational equations, we're going to do a lot of the things that we did in 9.1 and 9.2. So we need to identify undefined values, obviously. And then we're also going to be doing a bit of factoring and combining of terms through addition and subtraction. But our goal here is to figure out the solutions for x. And note with inequalities, our inequalities are going to be a set of numbers. So things like x is greater than 5, or 2 is less than x is less than 5. So our solutions for inequalities is going to be an entire set of numbers, as opposed to an equation, which is going to be just a single solution or a few finite number of solutions. So again, we'll start with solving equations. So let's go ahead and look at the examples below here. There are quite a few. So we're just going to do a couple of each here, and then I'll let you do the remaining in the notes, using the completed notes or just looking over your notes from class. So for number 1, we've got 6 over x plus 5 over 4 equals negative 7/4. So we'll note to start, x equals 0 cannot be a solution. Any other number can be, but not 0, obviously, because we have this 0 in our denominator. So our general goal is going to be to isolate x if possible. Otherwise, we're going to use kind of some other techniques. So for number 1, we can see that we've got two fractions with the same denominator, so maybe we'll just subtract that over, and we'll get 6 over x is equal to, well, negative 7/4 minus 5/4. It's going to be negative 12/4. So obviously, this is going to work out pretty nicely, but you can manipulate this proportion by cross-multiplying the numbers, or by simplifying. So maybe we'll notice that 6 over x is equal to negative 3, which means 6 equals negative 3x if I multiply both sides by x. And then solving that, we'll see that x is equal to negative 2, which is not an extraneous solution. So that is our solution. For number 2, we'll note that isolating x is going to be a little tricky because we have an x in our numerator as well as in our denominator. So what we can do here is, again, note our undefined values. So x cannot be 0. So what we can do in this case is multiply through by that denominator in order to eliminate it. So when we're solving equations for x, we typically don't want denominator variables. So if I multiply through by x, I'll get x squared minus 18 is equal to 3x. And then this becomes a pretty simple quadratic to solve. So we'll get x squared minus 3x minus 18 equals 0. And now we can factor or use the quadratic formula. I think this will factor. So x minus 6 and x plus 3. So x is equal to negative 3, or x equals, positive 6. Is the solution for this equation. So multiplying through, again, is going to be a useful technique for certain examples. So looking at number 3, 3 is very similar to number 1. Number 4, we've got a common denominator. So number 4 actually becomes really easy to solve. So we'll note x equals 2 is undefined. But if the denominators are the same, that means that the numerators are the same. So this just simply becomes 5x equals 3x plus 4, which means 2x is equal to 4. But that means that x is equal to 2. So that is our solution. And obviously we're done, right? No, we're not, because we get the dreaded extraneous solution, it looks like. X cannot equal 2, which means that this set of equations has no solution. So there is no value of x that will make this equation true. So again, be sure to check your solution against the undefined values. All right, so the last one we're going to look at is number 6. So for number 6, we definitely want to factor things, it looks like. So we'll have x plus 3x minus 2 on the left rational expression. And then on the right-hand side, we'll have x minus 8 times x plus 3, I think. Yep, that should work. And so now we can see that each one of these has an x plus 3, which means we only need to really multiply by the missing factors here on either side. You could also cross multiply, but you're going to get cubics, so I wouldn't recommend that. But again, it's totally up to you. But if we find a common denominator, we can do the same thing we did in number 4. Set the numerators equal to each other. We should note our undefined values before starting. So x is not equal to -3, 2, 8, and -3 again. So we've got 3 undefined values. And so let's go ahead and multiply by those missing factors. So on the top, on the left, we'll have 4x squared minus 32x all over x minus 8, x plus 3, x minus 2. And on the right, we'll have 7x squared minus 14x all over x minus 8 times x plus 3 times x minus 2. And again, our denominators are the same, which means our numerators must be the same. So that means that 4x squared minus 32x is going to equal 7x squared minus 14x. So again, something that you might want to do here that you should not do is divide by x. Because we don't want to divide by x because then we lose a solution. So again, whenever you're solving an equation, especially a quadratic or a linear equation, you just want to move everything to one side and then worry about factoring or canceling terms. So I'm going to move everything, I think, to the right-hand side. So we'll subtract 4x, and we'll add 32x. So again, these are just going to become 0. So we'll have 0 is equal to 3x squared, and then 32 minus 14 is 18. And then we'll note we can factor out a 3x, and we'll be left with x plus 6, which means x is equal to 0 or -6 are our solutions. And again, we don't lose the solution of 0 that you would typically lose if you just divided early by x. So note, if you're dividing by x, you're dividing out the solution. So do not do that to avoid missing an answer. All right, so again, 3 and 5 you can do on your own, and the homework will have a number of examples also. So for the next part, we're going to be looking at inequalities, and for these we are going to want to kind of treat them like equations and then worry about the inequality. So in other words, to start, we're going to kind of ignore the inequality and treat this like we were solving an equation, and then we're going to test points to see if it's true or false. So because our solution is going to be on the number line, the real number line for x, we can just do a quick test to see if our answers are correct, which means we don't need to graph these, although you can, and we don't need to worry about the signs changing if we divide or multiply by a negative. So note, if x is greater than 1, and I multiply the inequality by -1, then I'll get -x and -1 here, but our inequality changes also because the size of the numbers change, because negative numbers with a larger x value are actually smaller numbers. So we get this kind of reverse relationship. So we're going to avoid having to do any of that by kind of following this particular approach, which is solve it like an equality, figure out your undefined points, of course, and then we're going to do a number line test. So let's go ahead and do that. So instead of doing 1, I guess we could just do 2 first, which is find the undefined values. So we'll note x is not equal to 6. And what we call all of these values we find are critical points. So one critical point is going to be your undefined value. So for x equals -6, that is going to be a point of interest for us when we draw our number line. And again, what we're going to do here is we're going to ignore the greater than sign. And when we do one, we're going to solve like an equation. Because all we care about is when this is equal. And then we'll worry about the inequality afterwards. So if I have 3 over x plus 6 equals 3, well, I can multiply both sides by x plus 6. And we'll end up with 3 is equal to, distributing the 3, we get 3x plus 18. We can subtract the 18 over, so we'll get negative 15 is equal to 3x, and then dividing by 3, we'll see that x is equal to negative 5. And this is also a critical point, so maybe we'll call this one number 1 and this one number 2. So for this inequality, we have 2 critical points. So now, we'll go to 3. We can maybe call this step 2. So we're going to put those numbers on a number line. So negative 6 is smaller than negative 5, so be careful with negative numbers. And what we're going to do is note, what is our inequality now? So our inequality says that we are greater than, which means at our critical points, what we're looking for here is equality, and we do not have equality. So we do not have equals, right? So there's no equals here. It is a strict inequality, meaning that at our critical points, they are going to be open. And we'll note this one is always open because it's undefined. So your undefined points are always open. Your defined points are open or closed based on the inequality. And then what we're going to do here is we're going to pick values in between to test. So I'm going to pick a point that is smaller than negative 6, a point that is between negative 6 and negative 5, and then a point that is larger than negative 5. And so the values you typically want are integer values, but we can't get that in the middle. But we can get that here. So we could test maybe negative 7. And then on the right, definitely test 0 if you can somewhere. So 0 will pop up typically unless it's a critical point itself. Do not test endpoints or critical points. Do not test those because we don't know what the behavior is there and it may not be true. So do not test those points. Test points that are clearly greater than or less than your critical points. So we're going to test those values, and then in between, maybe we'll do negative 5.5. So we'll halfway between. So if x equals negative 7, we're going to plug that into our inequality. So we'll get 3 over negative 7 plus 6 is greater than 3. And we're just going to see, is this a true statement or not? So it looks like we get negative 3 is greater than 3. That is false. So it does not work there. So there is no solution in the region smaller than negative 6. If x equals negative 5.5, we'll get 3 over negative 5.5 plus 6 is greater than 3. So that's going to be 3 divided by a half. But 3 divided by a half is the same as 3 times 2. So we'll get 6 is greater than 3, and that is true. So that means we do have solutions between negative 6 and negative 5. In fact, any number between them will be a solution. And then 0. So at 0, we get 3 over 0 plus 6 is greater than 3. But clearly 1/2 is not greater than 3. So it is false. Which means that for our final answer, the solution is all numbers between negative 6 and negative 5, which we can write with a nice simple inequality. So x is between negative 6 and negative 5. And note it is strictly because our inequality is strictly. So this process is going to repeat each time. You're going to find your critical points. So those are the solutions and undefined values. And then you're going to test points in between. All right, so we're going to look at a couple more here. So we'll look at number 3, let's say. So we'll skip number 2. You can do that one on your own. So we'll note x is not equal to 5. That's a critical point. And then if I'm solving, I get kind of some weird behavior. So if I multiply by x minus 5, I still get zeros. All right, so we just get x is equal to 0, but that is our second critical point. And then I'll let you go from there on number 3. Let's go ahead and look at number 4, though. So number 4 is a little bit trickier. So we'll note that x not equal to 0 is a critical point. That's our undefined value. And now if we had x equals 4 over x, well, we can multiply both sides by x. So we'll get x squared is equal to 4, or x is equal to 2 and negative 2, which means now we have 3 critical points. So we have critical point 2 and 3. So that just means that we're going to have to test more values. So if we draw our number line out, we've got negative 2, we've got 0, and we've got 2. So 0 is undefined, so it's going to be open. But for our inequality, now we have an equality, right? Greater than or equal to, which means for our solutions, we can equal those. So these are going to be closed here at the endpoints. So now the question is, what is happening on each interval in between? So we've got negative 3, negative 1, 1, and 3 that we can test. So x equals negative 3 is going to give us negative 3 greater than or equal to negative 4/3, but that is false. So there's no solution there. Negative 1 is going to give us negative 1 is greater than or equal to negative 4. That is true. So we have a solution on negative 2 to 0. If x is equal to 1, we'll get 1 is greater than or equal to 4, which is false. And then if x is equal to 3, we'll get 3 is greater than or equal to 4/3, which is true. So we get this kind of alternating solution here. But now we have 2 regions, so we do need to be careful with our notation. So that means that negative 2 is less than or equal to x is less than 0, or x is greater than or equal to 2. So that is our answer. Note we can use interval notation here as well. So if you want to use interval notation, feel free to. So that would be negative 2, 0, union 2 to infinity. So either notation is perfectly fine to use. All right, so we'll look at our last example here, number 5. So we've got 2 undefined values, so negative 2 and negative 4. So we've got 2 critical points right off the bat. And then if I'm solving this, now we've got to find a common denominator. And then figure out what this expression is going to become. So it looks like we're going to get 3x squared plus 4, 12x. And then we need to distribute the minus, so be careful there. So minus 2x minus 4. And that's all over x plus 4 times x plus 2. So we can simplify the numerator first, maybe. 2. And let's see if that factors. So it'd have to be 3x and x. And I don't think we're going to be able to get 10, because 2 and 2 won't get us to 10, and 4 and 1 won't get us to 10. So this is not going to factor. So if it doesn't factor, our really only option left is to multiply. So we'll note that this is x squared plus 6x plus 8. So we're going to multiply x squared plus 6x plus 8 on both sides. Cancel those out. So we've got 3x squared plus 10x minus 4, and then 7x squared plus 42x plus 56. Moving everything over, we'll get 4x squared plus 32x plus 60, and I think we can divide by 4. So we'll end up with x squared plus 8x plus, 60 is going to be 15. So we have x plus 3 and x plus 5. Yeah. So x is equal to -3 and -5. So we're going to have a lot of points to test. So we've got -5, -4, -3, -2. -2 and -4 are undefined, so they'll be open. But -3 and -5, well, our inequality is equal to, so those are going to be closed. Okay. And now we're going to have to test points. So it looks like we could test -6, -5.5, -4.5, -4.5, -3.5, -2.5, and then over here I'll just test 0. So what we're going to see here, if x is equal to 0, we'll get 0 minus 2 over 4 is greater than or equal to 7, which is false. So it's not going to work here. And then testing our other values, I'll let you do that on your own. You'll see that we do get kind of that similar behavior of skipping over regions. So it will fail for -3.5, it'll fail for -6. And so our final answer, after testing those regions, is going to be -5 less than or equal to x less than -4, or -3 less than or equal to x less than -2. But keep in mind, this won't always occur. So there will be maybe weird cases where you do have overlapping regions and you just skip single points. So don't assume that they always skip each other, although they do in these examples. And we'll just note you could also use interval notation. So -5, -4 closed at -5, and then -3, -2 closed at -3. So either one of those is perfectly fine. So again, I'll leave the couple of examples there that we either started or skipped over for you to do on your own to check the notes online. But again, if you do have questions, let me know, shoot me an email, or drop by my office hours. So until I see